junction box will also be the other wire with 120 volts from a different phase. This is a separate circuit, so we can say A phase and B phase. So technically in this junction box, there lives 240 volts. So you do have to be careful getting your hands inside of a junction box that has both voltage systems. Now, to this outlet can only be one of them. Doesn't matter which one, I'll just use the one closest to the right-hand side. And this one can do whatever. It can splice and maybe take off down the road to another junction box to set up the rest of the multi-wire branch circuit, etc. So in the junction box, there could be more than 120. In residential, 240 would be the limit. In industrial or commercial, you might have a little bit more to deal with, 277 and 480. So to the outlet. Now, the outlet serves specific loads. So it's not just any outlet in the house. All right, but I'm going to pause here to see if anyone has any questions along the lines of what I've just laid out. So again, it's about terminal. Let me just reinforce that. It's about the voltage that's actually landing on the receptacle, not the one that has found its way into the junction box of the receptacle. All right, I'm going to erase this. It's on video, so if you want to come back to it.
My question is, is that how they get an outlet to become 240 by having two phases?
Okay, yes. You would bring both phases to the outlet itself. Correct. There are a few of them out there that have this kind of structure where it looks like a general, like a little receptacle. But the configuration of the prongs inside, and this is designed by NEMA, National Electrical Manufacturers Association. They are the ones that design these. And so you may see something like this with the ground.
It's in my washroom.
Yes, exactly. And then the plug cord, if we're staring at it, would be sideways like that. And then this one is hot. And this one is hot as well. A phase, B phase, and so we'd be plugging in 240. Older houses, well, not older houses, I should say houses that didn't get air conditioning units because it wasn't necessary, where, but you know, climate's gotten a little bit hotter, so now they're using wall unit air conditionings. Like for a living room, if you get a big air conditioner, but it's a wall unit, you could potentially be needing a 240 volt plug-in somewhere. All right, but let's talk about the difference between those. All right, because they do come up. Actually, if anybody needs that extra, again, it'll be on the video, but all right. I can always bring something back. Now, the things that you can plug into the outlets. It seems like it's only two things, but the second one is everything that you plug into outlets. The first one is lights. So the outlets that they're talking about right now, first of all, outlets in houses, not in a Marriott or not in a gymnasium or in a stadium somewhere or whatever, a bank. In a house, residential, apartments or otherwise. So 120 for outlets that serve lamps, right? Or lights. But generally, lights are going to be your lamps. That's the first one. All right? And like I said, they don't call them your general purpose outlets, but that's what they end up becoming. Just general purpose use receptacles in the house. All right, now early on, that was all they plugged into receptacles, but then things showed up. Televisions and microwaves and all kinds of other stuff, computers, etc., that people plug into the outlets. So number 2 covers everything else in the house that you can possibly plug into an outlet. Cord and plug connected loads that don't exceed 1,440 VA translates to watts, or VA. It means the same thing, but two different ways to express power. All right, wattage is measured energy use. So the electrical company, when they measure your energy use, they measure it in wattage, or it ends up being kilowatts because you use enough. But when you buy a piece of equipment and it's gonna tell you the nominal wattage, in other words, this is what it should produce when you energize it, then that is expressed in VA because it's nominal. So VA means the nominal or estimated wattage when we energize something, and wattage is actually the energy being used. Now, that is something that only electricians get exposed to. They get exposed to VA as the representation of wattage. Consumers do not. If you walk over to Home Depot and you try to buy a light bulb, it's not going to say 15 VA because a consumer would go crazy. Like, what is that? What does that mean? It says 15 watts. But it's not actually correct to say that that light bulb will have 15 watts. It's a VA expression because when I actually energize this light bulb, it could be 16 watts or 17 or 18 or even less. All depends on all the factors involved in where I plugged it in. All right, hopefully that's making sense. VA is going to follow us now throughout this almost whole course because everything is going to be expressed in VAs. So I can plug into these outlets, all right? What we are plugging into these outlets will not exceed 1440 watts. Now that's kind of hard to understand because you're like, well, what does that mean? Like, I can't plug in something that draws more than 4. How do I know what these are? Can I plug a television? Can I plug a microwave in? Can I plug a blender in? Well, the easiest way to figure this out is actually to do Ohm's law with it. Divide that over the voltage of 120. Right, it's going to be 12, but I think it's like 12 point something, or let me get the exact number. So let me just run it through my calculator real quick. If we do Ohm's law, divide that by 120. Yeah, 12 exactly, actually. 12 amps. 12 amps. So what this is saying is, for anything that you are going to plug into your house that doesn't exceed 12 amps, which is, like I said, everything you own. You don't have an oscillating fan or a computer or a blender or a microwave or a coffee maker that draws more than 12 amps. These things are generally somewhere around 4 to 6 or 7 amps. And that's on the high end. Your computer draws maybe 1.5 amps when you energize and you turn it on. Same thing with your television. Same thing with any light that you turn on in your house. Hair dryer, shaver, you name it. So that's why I call them general purpose receptacles, because that's where we generally plug in all these random things to. All right, so all of the outlets in our house that just sit on the wall waiting for you to plug a fan into or a television to, or maybe not use them at all, the maximum voltage that can be on the terminals of the receptacle is 120 volts. All right, this ends up just shortening up to branch circuits in houses, 120. But we'll get to when we can break that rule. Now, blenders and something like that, they fall with a little horsepower, quarter of a horsepower. Now, are there things in the house that are bigger than a quarter of a horsepower? Yes. There are things that are bigger than a quarter of a horsepower. So if you have things that are bigger than a quarter of a horsepower, then where you're plugging that into does not have to be limited to 120 volts. If I was going to be plugging in a large air conditioning unit that is going to draw more wattage than 1440 watts, then the outlet that it plugs into is not limited to 120 volts. I'll give you an example of one of those, which is our EV charging stations now. Right? It's a general outlet sometimes. It looks like an outlet, but these can be 240 for larger amperage connections. All right, so hopefully that made sense. All right, general purpose receptacles, maximum in a house, 120. And so, you know, now you can't have just general purpose outlets be 240. That's the main thing they're trying to prevent. All right, B. There's no questions on that one. We'll move over to B. B says 120 between conductors. Now that's different. 120 between conductors is hot, neutral. All right, this is not now going into 240. It's still our hot conductor and our neutral conductor, but there's a little bit of difference. Circuits not exceeding 120 volts between conductors shall be permitted to supply the following: the terminals of lamps and auxiliary equipment of electric discharge lamps. It's all going to follow lamps. These two are just going to be lamps of all kinds. It's the last one that covers some extra stuff. Cord-in, plug connected, or permanently connected utilization equipment. So what's the difference between these two? All right, in fact, I'll ask it. Can anybody point out the difference between those two? All right, the difference between these two is the permanently connected utilization equipment. Hard to put all those words together. These are not plug-in in the... This one is plug-in, so it's talking about the normal plug-ins, which was covered up here, so no worries on that one. But for pieces of equipment that you don't plug in to an outlet, that you hardwire into, like an air conditioning system on the outside of the house. All right, there's simply the difference between those two. Actually, not an air conditioning outside a house. Something like, I'm trying to think of a piece of equipment in a house like that gets permanently connected, but you don't plug into an outlet. And
the light. No.
Well, that's not a light. I should say that's not a light. Yes, lights always, but lights is covered in the first one. I was going to say, just came to my mind, is the range hood. All right, the exhaust fans. All right, exhaust fans. These are utilization equipment. The utilization is as an exhaust fan. That's how we're utilizing it as. And this cannot be 220 volts. All right, these are going to be connected to also 120 volt circuits as well. All right, I think those were the two that... The first one really lays out for us the full scope of general purpose receptacles in a house. All right, they're limited to 120. And because why are they limited to 120? Can they be more? Yeah, I guess they could be more, but this is generally all we plug into a house receptacle. Either it's lights or it's stuff that, as I said, this translates to less than 12 amps. All right, even a refrigerator. All right, even the refrigerators, if you look at the amperage on a refrigerator, 12 amps is the max size refrigerator amperage. Standard house, refrigerator going into that. Not like a, commercial restaurant refrigerator. All right, this is not talking about any commercial buildings or anything like that. Outlets in commercial buildings, that's a different rule. All right, this is only for residential. An outlet in a commercial building could have more than 120 volts because of what it needs to be for the equipment's being used in a commercial or industrial building as well. All right, now honorable mention was C. As I said, not so concerned with the C part of this as far as, because we focus heavily on dwelling units, and for reasons that are good, because residential has a lot more rules. Commercial buildings don't have a lot of rules as far as locations of receptacles and voltage that they have to be, or industrial buildings. All right, C is talking about when can circuits exceed 120 volts? Because the way A and B lays it out, it says this. It says any branch circuit coming off of a panel should be 120 volts. But that becomes hard because there's a lot of things out there that are going to require more than 120 volts, and they will be branch circuits. All right, for example, machines. All right, I'll show you where they cover it. Machines, though, anything like that, it might need 240. So if you look at this particular Article C, it's covering specific 277 volts to ground. All right, circuits exceeding 120 volts nominal between conductors and not exceeding 277 nominal to ground shall be permitted to supply cord and plug connected or permanently connected equipment of the following. Now, one of the things that you'll see of the following is it's literally all lights. All right, these are for commercial buildings with lights. The lights in commercial buildings tend to be 277. So do the lights in industrial buildings. But this is where you can run into that problem that we talked about yesterday, where I have two different voltages in the system, or in the building. All right, the commercial building might be using general purpose outlets to plug in computers and etc. at 120, but now all of the lights in the buildings are being fed off of 277. All right, and it's the bigger lights. This is where the electric discharge luminaires with ballast internal come in. All right, large LEDs with drivers inside because it's producing a lot of wattage. Old incandescent, still honorable mention, but I don't think these light bulbs are around as much these days. And so on. You know, you're starting to talk about these large lamps. If you probably have not heard this term yet. So let me explain this term because semi-important, I would say, as electricians to know the three types of light bulbs that they sell based off of the base of the light bulb. All right, so, yes. Oh, absolutely. Thank you. All right, we got electrical discharge. Good. Let me explain these 1 second. Electrical discharge luminaire with ballasts. So let's talk about the light bulbs first. There's three types of light bulbs that we have. All right, I'll give this a fresh page if anybody wants to write this out. And then we'll talk about the bases of the light bulbs. So the original light bulbs, this was the incandescent light bulb that had a filament inside, the one that Edison created. That name will come up here in a second. So this is incandescent. Great light bulb, incandescent, something like that. Great light bulb, I think there's an A in there. I may have spelled that wrong. Good light bulb, but problem with this light bulb is this is the old light bulbs. If you maybe you guys are old enough to remember, some of you, you go and buy a light bulb and it was a 75-watt light bulb. It was a 100-watt light bulb. All right, because a lot of energy went into this light bulb to create light, and it lost a lot due to heat. In fact, it was something incredible as far as energy loss to light produced. Something like 90% of the energy invested into creating light was lost to heat. This was heat loss. And then only 10% actually converted to light. So this why it's required 100 watts to produce X amount of light, and then it reduced a lot when we went to LEDs. All right, so this is where you had these large wattage numbers. So somewhere, and I don't know when, they tried to make light bulbs a little bit more energy efficient. So they came up with another light bulb, and it was twisty like this. And this was a CFL. All right, this was a compact fluorescent. Try to spell that one. Probably spelled it wrong. Fluorescent. The fluorescent had another style light bulb that was around a little bit longer with it, which was the tubes. All right, the tube light bulbs, and they had the little pins on the end. All right, maybe you've seen them, maybe you've changed them out. You have to twist these out, and they go on a little bit a tombstone on each end. They're called. So you have to twist these out. Now, here's the thing with fluorescent that was different from incandescent, is this had gas inside. All right, the fluorescent was filled with gas. So it wasn't just apply voltage to a filament that had resistance, and then you would get light. Again, you would get a lot of heat off of this. When I was a little kid, you did not touch a light bulb that was on. You turned it off and waited like 10-15 minutes before you tried to unscrew it. But fluorescent was different. It had a bunch of little gas inside of this, and so you had to light it. You had to literally ignite the gas inside the light bulb to get light to come out of it. Well, that required a lot of energy only up front, only to get the light bulb started. Then it didn't require a lot of energy to maintain the light bulb on. So they brought in these ballasts. All right, these ballasts. And these are like a giant energy boost right when you turn on the light bulb. And the ballast gave you a lot of voltage up front, ignited all of the gas inside, and this is why you can tell when these are going bad, because they start to get burnt on the ends because of all the energy that's on these ends of the light bulbs. Now, fast forward to today, they've created the better light bulb of all of them, which is the LED, and LEDs don't require a lot of energy, so no ballast anymore. LEDs produce the other way, where 90% is actually going to give you light, and only very little, 5%, something like that, is lost to heat. All right, I know it should be 10 just to fill in the other 5%, but another 5% is going through the computer driver. So this is why you look at the same light bulb now, it's only 15 watts. So in the world of lighting, you have LEDs, much more common these days, but a lot of older buildings that haven't transitioned to LED yet will have these fluorescent lights. All right, the tube lights that you might see if you walk into a Target or something like that. Now, again, these days, the long tube lights are probably LEDs, especially a Target that has the money to change out already. But if you go into like an old auto body, you know, like Auto Parts or AutoZone or Napa or something like that, they haven't updated it, though you'd probably see fluorescence or something like that up there. So that is called an electric discharge ballast, and so the lights with it are called electric discharge lights or luminaires, with integral, meaning the ballast comes with it, and in the event of the light going bad, then we change the ballast. So it was a step up from the old incandescent light bulb. These used a lot less energy, all right? It reduced the amount of energy, but we weren't done. LED made it even better. Now, there's another type of light bulb out there that also uses a ballast, and it's called, they're called high discharge lights. And these are the ones you might find at a stadium or an auditorium. They sit up way high, right, in the bays of warehouses too. The light bulb inside of here produces a lot of energy. Sometimes these are hydrogen or different gas filled, I don't think hydrogen, but different gas filled inside of these light bulbs. They also require a lot of energy, so sometimes they come with a ballast as well. Now, if you work with a lot of light bulbs, I got to work with a lot of light bulbs, so I know all of the world of light bulbs. Some people don't work with as many light bulbs, so it is something you're not as knowledgeable on. But I did a lot of warehouse retrofitting, and so we had to change a lot of lights up there. Now, to the base, all right, to the base of the light bulb. There's 3 bases. I'm going to get rid of this. Again, it's all on video. There's 3 bases to the light bulb. There's the little one. I'll try to draw the light bulb. These have changed these days, but these are called candelabra. And these are small. This is very tiny, small base. All right, these go in like, actually I have them here on my ceiling fan. Small base. Tiniest of little bases, right? Small wattage too. Then you have your standard light bulb. Your standard light bulb, the base, now we're talking about the base. The standard light bulb is called an Edison, or Thomas Edison base. These are regular. This is your average light bulb that you buy, you know, for your normal plug-in lamps and stuff like that. Then there's a third one that not a lot of people get exposed to, and not a lot of people know the name to. The name is in this article I just went over. It's called a mogul. a mogul base. All right, and the mogul base is just a larger base. All right, these are for those high pressure sodium lights and stadium lights, I like to call them, because that's how people associate them. It's called a mogul base. So those are the three bases to light bulbs. I'll pull it up for you guys so you guys can see some of these light bulbs. Some images on them, but all right, these were something more like this type of light bulb, a little bit more. And you can see the price on that. All right, again, these are all LED retrofit these days, so these, but you can see the voltage, 277. It's called a metal halide equal. This was the older model. The older model, look at the wattage on the older model, 320 watts. Nowadays, 54 watts for the same amount of output, which is 10,000 lumens. All right, and there's the base down here. You'll see mogul. All right, and it's telling you the measurement. It's saying screw in, I'm not sure you can see it on the whiteboard that well, but it says 39 millimeter in diameter on the base of that light bulb. Again, everything is now LED, but these lights, back when I was changing them, they were this model here, the 3200 watt metal halide, and that required, going back over to it, that required these large electric discharge ballasts for 320 watts of light. But again, big changes these days in the world of light bulbs, big changes in energy demand, and now you get the same output for only 54 watts. And by the way, that's the bill. The bill from the electrical company is based off of the wattage that you're using up. So a building that went from 1,000 lights that was using 320 watts each light to those same 1,000 lights now only using 54 watts is an incredible savings in electric bill at the end of the day. That's why it's very worth doing these retrofits with LEDs. It is actually a very good place to make some money, which is doing retrofits. I'm not sure if that's still, I think a lot of people have cornered that market, but all right, we'll finish up this article. Not a lot that I have to, right, there's the LED retrofitting kits, all 277 as I pointed out. So let's jump down here for a second and jump over to article 210.7 unless there was any follow-ups to that stuff. Really, the takeaway that I want to make sure you guys understand is your general purpose receptacle in houses, maximum 120 volts. In a commercial building, they can exceed 120. If that's what you picked up, like that's what I'll remember about it, then great. That's a pretty good breakdown of everything. If you caught the little bit extra with the 277 and the lights, good. But if you got that part of it, we've landed on a good understanding.
So where does the 240 comes in when for the washing machines and for the car chargers?
As far as receptacles that are allowed to.
Yeah, because it's still in the dwelling units. So I don't know how can it be up to code if it's 240.
So remember, all of those things that we mentioned are going to be higher wattage than 1440 watts. So this is only for things that are 1440 watts or less. So if I'm going to plug in a dryer or a range or a car charging station, EV station, that's 10,000 watts or 7,000 watts or 6,000 watts, then the receptacle that's going to plug into can exceed 120 volts. Sounds good?
Yes, sir.
Okay. So yeah, for anything that is bigger than 1440, remember what 1440 watts translated to 12 amps. For anything that's larger than 12 amps, then the outlet that it plugs into can be larger or have more voltage than 240. All right, but what happens in a commercial building is you'll see a receptacle and it won't have 120 on it. it'll have 277 on it. But that's to plug in industrial lighting or anything like that. Usually they're not down low. I mean, usually that's kept up and away from, you know, just a person that doesn't know, sees an outlet and plugs in their phone charger into it or something like that. It could be dangerous, yes. So you usually put these in inaccessible areas if there's the public, the general public is nearby. So this might be up high and in, you know, the top of the building in a junction box, the outlet sitting in here, and then the light fixture is plugging into it. All right, this is probably how you should set it up better, just given that that receptacle is going to have 277 volts. All right, so in an industrial building or in a commercial building, you can find receptacles that have 277 on it, but they're for industrial lights.
Wait, so how would you get the 277 to the receptacle?
Okay, so let's paint a picture of that. Did I have a page? Where was my page? There we go. So you would have a panel. Now here are the options with running anything, but more than likely in a commercial or industrial area, we're going to run conduit from this panel. And we're going to head over to this junction box up in the top of the ceiling somewhere. We'll do all the supports in the correct ways and etc. Now from here, let's explain what 277 is. We'd have a single pole breaker in here, and we'd run a wire. Now, the wire would be, let's go back to yesterday for a second. It would be one of these. It would be brown, orange, or yellow. Just one of them. Because in this panel, each one of these is 277. You probably cannot see that well. I guess I'll put it in red. 277 on A phase, 277 on B phase, and 277 on C phase. So all I need is one of these phases, not both, just one, and a neutral. Now I don't have brown, orange, or yellow in my pen, so I'd run that. Now I'll go over to the panel I was setting up here. I'm just going to do it in black and red and blue. I'd run the hot, a neutral, and now the hot and the neutral are available up here. But you can order MC, by the way, with brown, orange, and yellow, and all the same as the black, red, and blue systems. You can order MC cable just like Romex, 12.2, 12.3, 10.2, 10.3, 8, all the sizes. But the other thing about MC cable, unlike Romex, is you can actually get one with 3 phases. You can get brown, orange, yellow inside the MC cable with a neutral and with a ground on it. Or, you know, any combination of those, just like with Romex. But the addition is you can get the 3rd phase into it. And that's it. There's the 277. We'd get I'm going to talk about the outlet in a second. There's something this outlet does have to have. And that's it. You would run hot to one side, neutral to the other, and then my light fixture would have a cord on it and plug right into it. And there would be the setup. Now, probably this is going to run through some type of lighting control system. You guys have not gotten into controls yet, because I don't want this light always on, so I don't want this outlet to always have power. But, you know, the lighting control system is also falling under energy management, which these days every area has their own rules. You guys have rules in California that are different from, you know, somebody in Maine, just because of energy in both places being a little different. So controlling of the light on and off might not just be the outlet always has power, but in general, that should give you an idea. Now, also what's more than likely, let's just kind of clean this up a little bit, is not have an outlet at all. Not have an outlet at all, because you'll see it says, let me go over to where it says it. There was one here, plug-in or, oh, I lost it, where it said the same thing, either plug-in or hardwired. And I'm losing, I lost the location of it exactly. But anyway, it means that you can just mount the light right on the junction box, right, and just splice in. Be better to just splice the hot from this one and the neutral as well, and not have an outlet at all. But again, it is a branch circuit. It does exceed 120 volts, but it's for lights. In other words, the general purpose receptacles in the walls that, again, a commercial building could have a little bit higher voltage if they're serving the purpose of only lights. Now, if we look at Article 210.7, this one's going to be a little bit confusing as far as what it's saying. So let me come over to Article 2. We're going to keep talking receptacles. If you had any more receptacle questions, line them up. We'll keep talking receptacles. But this one is because it doesn't lay it out very clearly. So, and it follows 210.6. So 210.6 said receptacles for general purpose use in residential have to have only 120 volts on them when you're going to plug them in. But here's what happens sometimes in a house. All right, I'm going to give you a scenario that happens a lot, especially in new homes. So you'll have the sink. All right, maybe you have this in your house. All right, you have your sink. And these days, a lot of sink is really good for the plumbing, even though it's expensive. But you'll have a garbage disposal. All right, a garbage disposal. And that's the little thing that turns and destroys all the food and then sends it out into the plumbing, all grinded up, and so it helps. And because the sink is here, and this is just a layout of design, all right, because the sink is there, right next to the sink, if the house is going to have a dishwasher, it'll have it right next to the sink because, you know, you have your plates in here and you're putting them right in the dishwasher. If it was farther away, it'd be a bad design. Now, 100% of the time, no, but I've built many apartment buildings and this is the layout. So here's what happens. This has a cord on it, and so does the dishwasher. The dishwasher also has a cord. Garbage disposal cannot be plugged into an outlet that's always on, because then your garbage disposal will be always on. So you want on and off control of the garbage disposal. Your dishwasher, different. Your dishwasher only is going to turn on when you press start, and it'll turn itself off. So that receptacle can be always on. Now, because these two find themselves in the same area, we always do this setup where we supply under the sink with a duplex receptacle for both the garbage disposal and for the dryer. Doesn't matter, or sorry, dishwasher. Doesn't matter which one. I didn't put here dishwasher. And the garbage one can go to the, again, doesn't matter which one. Up or down, doesn't matter. But ultimately, one plugs in and the other one plugs into that one. All right, so good so far. Now, what usually gets set up is there's a switch here. And that switch is going to control, make it easy, I would say it controls the top one. But the power to the bottom one is going to be separate and not controlled on the switch. All right, just trying to give everybody a visual layout of what's going on, right? You don't have to understand how we're doing this yet. How has any of this happened? But I have duplex receptacle, meaning I have one plex and another one. I'm plugging something up here to the top one that I'm going to switch on and off. And I'm plugging one into the bottom one that I'm not going to switch on and off. Now, here's the other situation here. There's another situation. And that is that the garbage disposal generally produces somewhere around 12 amps. Well, maybe less. I would say maybe not that much. Maybe 8. But let's say 10, right? Just to be on the safe side. And your dishwasher, when that operates, that does sometimes produce somewhere around 12 amps. All right, so if you're looking at this, you have to now understand something. And that is that this receptacle cannot come from one breaker by itself. Forget that the fact that they're, split and one's going to be switched. I could do that off of one breaker if I wanted. But I can't have one breaker down there because 12 plus 10 equals 22. So that exceeds 20 amps. And I cannot put a bigger breaker here because I'm not allowed to do that. We'll go over amperage limits. I think it should have been covered in Code A. This is, I think, why you come over to 210. To go over some of the 15 amp, 20 amps, and 14 gauge, 12 gauge wires. Maybe, I forget exactly. So if we lay this out, all right, if we lay this out, now we're going to need 2 circuits over here. All right, I'm going to actually need 2 breakers. So 1 breaker, 2 breakers. And now, before we even get down to the outlets, understand the situation. A phase, B phase. That means 120. Means 120. If you measure between both of these, 240. Both of these are going to terminate on the receptacle, meaning this receptacle is going to have 240 volts on it versus 120, seemingly breaking the rule we just read that said maximum on the receptacle for garbage disposal 10 amps only, so that falls under the wattage. 12 amps over here, that falls into the wattage range, so both of these should be limited to 120. And we have 240. Now, does all of that make sense so far as far as what we're dealing with, what we've run into as a situation? All right, I got to switch the top one from the bottom one. The bottom one's going to be separate as far as being on the switch. I have 2 things being plugged into this that are exceeding 20 amps. I have to bring 2 circuits to this outlet, and now I'm dealing with 240 at the outlet physically. There's 2. So if all of that is making sense, let's head over to, we'll do this a little bit more close up using this close up outlet with the article above it. This article deals with that situation. All right, so let's read it. It says if 2 or more branch circuit supply devices or equipment on the same, we'll pause there. Actually, let's pause it at equipment. Let's not go any further. Let's break that part down first. If 2 or more branch circuits supply this device, meaning one breaker, 20 amps, other breaker, 20 amps, I have 2 or more branch circuits now supplying one side of the receptacle, other side of the receptacle. So again, between both of these, if I was to measure, I have 240. So this is saying you can now exceed the 210.6 limit of 120 if you follow a few of these rules here. All right, it's saying in a situation, this is the most common that I know of, which is garbage disposal dishwasher. Almost anyone that builds houses is going to run into that these days, because almost all houses these days are coming with garbage disposals and dishwashers. And they always live in the same area, and we always have these outlets to deal with. And they're always in a really cramped area under the sink, which is not fun to work under. All right, so 2 or more branch circuits are supplying this device or equipment on the same yoke or mounting strap. Let's unpack that. What does it mean to be on the same yoke or mounting strap? Means they're talking about a duplex. All right, it does not say, I wish the code book would just say on a duplex receptacle, but it doesn't. It says on the same yoke or mounting strap. All right, just laying it out in a more technical way. Where's the yoke of this receptacle? It's the metal part behind it. It's a little, this part. That's the yoke, not LK like an egg, OKE, yoke. All right, this is where our ground is connected to that yoke. So is that little center screw. It's connected to the metal of the yoke. This yoke has 1 plex and it has 2 plex. Again, that's what we call a duplex receptacle. So if you're gonna have this, same rule as a multi-wire branch circuit rule. Because guess what? We're running one neutral shared between both sides of this. We now fall under the rule of being a multi-wire branch circuit, 2 or more ungrounded conductors with a shared neutral. So we have that rule to deal with. But here it's also following up and saying, don't forget, these breakers have to shut off at the same time. There's the way you can get away with this. The way you can get away with this, bringing now 240 to this outlet, and I'll explain why it's not 240. Technically, it's not 240. But the only way you can get away with this is, just to get that neutral out of the way, if both of these breakers shut off at the same time. So again, you have the problem you're dealing with where these two breakers have to be side by side. All right, you have to put these breakers side by side. So that's one of the things that you have to do. One is breakers got to be side by side because the breakers have to both shut off at the same time. Now, who can tell me the other thing that I have to do to this receptacle to make it operationally safe?
Break the tab off.
Very good. You got to break the tab off of this receptacle to split the two sides from each other. If you don't do that, you have both sides still connected to each other, and now you have A phase and B phase, and it's going to trip your breakers. It's not going to trip both. It's going to trip one of them. Unless both wires were exactly the same size, same gauge. I mean, it'd have to be a perfect situation for both to potentially trip at the same time. All right, good. So that's the first thing, is we got to break this tab. Very easy to break the tab. Now you've separated the two plexes from each other. And so now, let's tie it in here. Now we can have our switch. Right there, I'll draw the switch in here. Now this will be the one controlled by the on-off switch. So this one will be switchable on-off. Only need it when you flip on the garbage disposal, or only flip the switch when you need the garbage disposal, I meant. And this one's always on, so dishwasher is ready to go. Now, obviously, somebody can mistakenly plug those two in, but notwithstanding that. Now, there's another problem. There's actually another problem here. So here's my question. This white receptacle that I have these two wires on, right, assuming that I've broken the tab off here, and assuming I got both of these breakers side by side, is there anything else that you are seeing from what I have on the board? You have to see what I have on the board to know this answer. That could be a problem on this receptacle. It actually is a code violation, and you would fail your inspection, and it's one of the things, the other things the inspectors look for. One, they look for both breakers being able to shut off at the same time. That's really their main concern. If you didn't break the tab, you'll find that part out. They don't really care. You'll see an explosion. They would care, but you're going to turn power on, and so it would happen. There's another thing they're looking for. Can anyone go ahead?
The receptacle's not rated for 240 amps.
Excellent. Yeah, the 125 down here rating of this receptacle. That's why I have this other one side by side with it. Not just to show you the NEMA version. This is the one that we were just talking about that you pointed out, Gerald. This is the type that could have 240 on it. Antoine, to your question, this would be for something larger that required 240. Let's say my air conditioning wall unit, that, you know, the window one that I want to plug into this outlet. This outlet could be now 250 volt rated. Doesn't violate Article 210.6 because the air conditioner is going to draw more wattage than 1,440 watts. So that would be the other. Go ahead.
You're saying that we can only use the one on the right if we're going to do the garbage disposal?
If you're going to use the garbage disposal, now let me point two things out on it. I just did not find the. You would still need the original NEMA configuration. Not sure if you guys have talked NEMA and receptacles yet. But when you guys order receptacles, not when you walk into Home Depot and look for a receptacle. Home Depot is a different world. When you order from a supply house, electrical supply house that specializes in electricity, When you call, even when you walk on the counter, sometimes they want you to know these things. When you order receptacles, you don't say, "Hey, I need outlet receptacles or 120." You say this number to them. Sorry about that. I blocked it. You need a NEMA 515R. 5 means this configuration. It literally means this one straight, that one straight, with the ground under it. A different configuration, like the one on the right-hand side here, with this configuration, a side option with a straight option and a side option with a ground, is a NEMA 6 configuration. Dash 20, because this is rated for 20 amps. This one is only rated for 15 amps. R, both of them, because they're the receptacle version. If you wanted to order the plug, then you would, because we have to do this a lot for machinery, you would say, hey, I need a NEMA 6-20R and 6-20P. Meaning I need the receptacles and I need the plugs for these. So to answer your question, you would not get this exact you would get a NEMA 5-20R rated for 250 volts. That would be the one you'd order from the supply house. And by the way, NEMA has a long list of NEMA configurations, and all of them mean how the little lines look, how the little terminal points look. A NEMA 5, straight line, straight line. A NEMA 6, the little side like this, plus plus the side one here. I lost my train of thought there.
I just don't get why it has to be rated 250 volts if it's not going to see actually 200.
Right, because good question. Right, so the question is, why does this need to be rated for 250 volts? Because this receptacle can only handle 125 volts on it, a maximum of 125 volts on it. You are terminating onto this receptacle 240 volts. So this receptacle would not go with this system because on the receptacle is 240 volts. Even though each thing plugged in is only going to get 120, but on the terminal points of the receptacle, on the hot side, because here's what happens, right? If this was like this, right? Because I can also do this like this. One breaker, send a wire to a junction box, and then put one hot, I'm going to design this in a way it's not, so have a switch where this hot goes to the switch and controls the top one, and this one just gets spliced and goes straight to the bottom one. Right? So in this case, we have 120 at the receptacle, total between both sides. Both sides are 120. I can't measure between here and here. My meter's going to say nothing. It's going to say OL, out of limit, or it's just going to try to give you some crazy number. Because you're just measuring the same phase. There's no difference in potential. Your meter is not measuring a difference between anything. Now, is this done? Sometimes. Sometimes it's done this way. When can it be done this way? When your garbage disposal and your dishwasher together don't go past 20 amps. So maybe for like apartment buildings that might have small garbage disposals, small dishwashers, right? Where you have our garbage disposal might only have 8 amps. Our dishwasher, I mean, it's got to be low because even 10 amps on this dishwasher is 18. And this is not a good idea to load 18 amps on a 20 amp breaker. You will have future problems. And the engineer, designer of this is going to separate this circuit at that amperage. Now, if this dishwasher happened to be, let's run the numbers a little bit lower. Say we got 5 amps on my garbage disposal and only 8 amps on my dishwasher. Now, total between these two is a 13 amp. Okay, now I'm comfortable putting it on a 20 amp breaker. I would not be comfortable on a 15 amp breaker, too close to 15 to 13. Right, now these all get into semi-nuances. Like you got to know a little bit more than extra to be able to design. You guys are not in the design phase yet. You're more in the understanding what I'm seeing. You know, if I open up an outlet and I see two wires on it and they're both of different phases, to know why that is. So a lot of times you can't set it up this way. A lot of times you are forced to set it up with the separation of the loads. One breaker and then another breaker, where switched for the top, straight run for the other one, and now measuring with my meter between both of these, it's not open line anymore. Now my meter reads 240. And now the 125 is too low of a rating for the voltage on this device. That's why we go through the understanding, because it doesn't really say it so straightforward to us. You got to kind of piece this thing together from a couple of articles. All right, but hopefully that satisfies the question.
Yes, sir. Thank you so much.
Good to go. Absolutely. All right, so next time you're in Home Depot, you don't have to go to Supply House. Since you have, good thing about Home Depot is you can just grab stuff and read them. Go and read NEMA ratings, NEMA numbers. And now, you know, you don't have to memorize them, but get familiar with the NEMA number to the design of the outlet. Or configuration is what it's called. All right. All right, next article that follows. If anybody has any follow-ups, good to go. If not, let's just also make sure, you know, I would highlight simultaneous disconnect. That's one of the main things to have focused on there. The ungrounded supply conductors shall be provided at the point of which the branch circuits originate. So again, whenever it says the point at which the branch circuit originates, that's the panel in most cases, but why doesn't it say panels? Because not 100% of the time is it that where the branch circuits originate is a panel. Sometimes it's other things like disconnects and control panels or something like that. All right, so again, it's a law book that has to cover a lot of. All right, next thing's GFCI. I think this is another reason why you guys come over to this article from Article 210 or from Code A. Not a lot that I have to explain on this article, just a couple things. So let's head over to Article 210 GFCI. One I do want to go over in detail. I don't know if it gets covered 100%. Again, always my focus is why, of what a GFCI does, why we have it, and what it works to do. But here's the thing with this article. All right, this is a very easy article. This is going to be like AFCI. AFCI is the same as this one. Except there's a little bit on the breaker to outlet setup for the AFCI. This one does not have it. So all this article says, and all this article is for, is to give you an understanding of where GFCIs are located. Where you have to have, if you have an outlet, all right, GFCI, this outlet has to be a GFCI. Now, there's a very important thing that we're going to come back to for GFCIs, which is here. All right, it's for AFCIs, does not have this. All right, AFCI does not have this. And that is that the GFCI, while rooms may call for it, right? Let's go into the article. The article is this. Two things separate the GFCIs. Dwelling units, so mandatory locations of GFCIs in houses, dwelling units, and mandatory locations for GFCIs in anything else that is in the house, a church, a bank, a school, all right, other than dwelling units. So here's the first part. Any question that you get asked is going to come from that. Which of the following requires a GFCI? So you would come through here and see that. All right, bathrooms, outdoor spaces, garage, crawl spaces. If we're in a dwelling unit, continues over here. Basements, kitchens, boats. Now, small focus, which again, I think you guys covered this last module. You should have this highlighted. If not, I would. Which is near a sink within, any receptacle within 6 feet of a sink. This increased. When I was a young electrician, this was only 3 feet. Now they've extended it to 6. In fact, the first time I started teaching this class, I was saying 3, and somebody pointed out like, hey, it's 6. And I had to do a little bit of research, and yes, they changed it from 3 to 6. Same thing with any receptacle near a bathtub. If the receptacle is within 6 feet, many bathrooms are very small, so any receptacle in the bathroom is within 6 feet of either the sink or the bathtub. So that has to be GFCI. But there's a theme, right? You can almost common sense GFCIs. The theme is water, right? That's what they're focused on, water. Anything that you see here in either one is referenced around water. Wet locations literally says it here. Bathtub, boathouses, water, water. Sinks, water. Kitchens, water. Prepping and food at water. Basements can get flooded, water. Garages can get flooded, water again. Out crawl spaces under the house, water. Outside water, bathrooms, water. So in commercial buildings, then there's different kinds of commercial buildings where you have aquarium, bait wells, you know, fishing shop or whatever. Aquarium. Locker rooms, right? That's not a residential. Sorry, I meant the locker room. Rooftops, not usually in the house that you can get on the roof, but restaurants, buffet areas. So there's the big separation. All right, the big separation is residential versus other than residential. But here's the thing. All right, this is really important because you can fail an inspection. All right, now I'll give you a situation. All right, in a kitchen, here's my refrigerator. So it's in a kitchen. It's going to have a receptacle behind the refrigerator. I'm drawing it like that, but we're Superman and we can see through the refrigerator. Now we see the outlet behind the refrigerator, meaning the refrigerator is going to get plugged into that outlet. So does this outlet in a kitchen have to be GFCI?
No.
No. GFCI shall be installed in a readily accessible location. So for any one of these, bathrooms, garage, outdoor space, etc., kitchens, doesn't matter whether it's residential or not. All right, the information for dwelling units here, other than dwelling units, doesn't say it because it's already covered here. All right, this is the main important part. GFCI must be readily accessible. So even if you're putting an outlet in a, again, kitchen, it happens twice in the kitchen. It happens for the refrigerator, and it also happens for, this is your oven, or range. Again, this is the one, and you have the exhaust fan, or it's called a range hood there. Usually you have a cabinet up here, right? And sometimes this is a little bit of a different design where you'll have a microwave here as well, right? Not always, not all houses have the range hood with the microwave combo. It does happen plenty, right? And so there will be a receptacle in this cabinet for the microwave. Open up the cabinet. There's my receptacle. The microwave gets, even if it's below, if the microwave's below, then the cord gets fed through. I guess I didn't design this right for the drawers and the microwave. I guess it would be like this. So the drawers above the microwave. So this is another one that, again, the ones that I'm aware of, that again, it's in a kitchen, it's an outlet in a kitchen, but does not have to be GFCI. Again, main important thing about GFCI is readily accessible. You have to be able to reset it, or at the very least get to them. And remember the rule to readily accessible. Readily accessible, definition from last module, is not requiring me to move anything out of the way or get a ladder and get on top of the ladder. Accessible, yes. If it's just accessible, then I could get a ladder or move something out of the way. But readily accessible means at the touch of a finger, at the stretch of my hand, I should be able to get to that.
If you had a receptacle like underneath the sink.
Right, exactly. Exactly. That's the other one. Going back over here. Yes, this garbage disposal dishwasher receptacle also just gets not readily accessible. Actually, I don't think they cut. I don't think they count that one as readily accessible. I've only ever seen it be a straight receptacle, not a GFCI. It's also not a good idea to put a GFCI with a little motor. GFCIs and motors don't work well together because motors are actually, so let's go into a GFCI, right? I'll explain this part with this, and we only have a little bit of time, so this shouldn't be too long. What does a GFCI protect, and why do we have a GFCI? Because what a GFCI protects from is only two things, and that is a ground fault. And so here, let me unpack these two words a little bit for you, just so you guys can have a better understanding of it. Ground fault and a short circuit. Now, at the end of the day, all short circuits are ground faults, because at the panel, the neutral and the ground are bonded together, and so it just uses the GF, ground fault, umbrella term. But these are actually two different faults. A ground fault is when the hot and the ground come into contact with each other. All right, this sometimes happens when, you can cut a wire and do that, but a lot of times this happens when the hot touches some metal. All right, some kind of metal. It's usually when a ground fault happens. The short circuit is when you've shortened the circuit. Remember what a circuit is. We talked about that yesterday. Breaker to the load, and then neutral. That's a circuit. So a short circuit is you bypass the load, and the hot and the neutral have come into contact with each other. All right. Technically, what's really happening is you got rid of resistance. All right. You didn't, because this happens with the load still plugged in, but somewhere along the line, the load shortened. All right. So that's why a short circuit is different from a ground fault. All right. But they use the term for both of these. Now, we already have something that protects against both of these. Can anyone tell me what that is? It's already in the circuit, protecting from a ground fault and a short circuit.
Our breaker.
Very good. Our overcurrent protection device. Overcurrent is a short circuit and a ground fault. But overcurrent is one extra one, which the GFCI does not cover, and I said it yesterday, which is overload. Meaning, to this GFCI, you plugged in a load. Let's say this GFCI is on a breaker, right? The circuit that's feeding it is a 20 amp breaker. Let's just say that. Even though this one isn't, actually, let's say the right one. This is a 15 amp breaker. Because of the configuration, that's a 5-15R. Not a 20. A 20 would have this little line here. Again, the Neiman numbers to get familiar with, pretty good, just so you can know stuff like that. But let's say I plug in something here that's 25 amps. This GFCI is not going to trip. GFCI is not designed to worry about the amperage load that you've plugged into it. That's going to be the job of the breaker. So the breaker already does not only ground fault short circuit protection, but even extra, covers the overload. But the problem is time. Response time. Response time on a GFCI is a lot quicker than response time of a breaker for the same fault, because, right, here's what they're banking on, and here's the worry. This is going to be different when we talk about AFCI, which we'll talk about tomorrow. They're worried about you plugging something into this, and between here and here, where the human stands, touching it, bathtub, hairdryer, all those, toaster in the tub, that's where the human is. They're worried about that, the cord to the load, and you getting shocked, ground fault, something. They're not worried about somebody cutting this line over here and a short circuit and a ground fault happening. The breaker's going to cover that. They're worried about somebody getting shocked. Now, if somebody gets shocked and you don't have a GFCI, if somebody gets shocked here at the load and you don't have a GFCI, the time it takes for that short circuit to get to this breaker is going to be whatever, somewhere around, we can just call it X, but somewhere around 1 to 2 seconds. Towards on the higher end of that, if the distance is further. Short circuits happen very quickly. Ground faults have an increase in amperage very fast. These breakers will trip quickly, but the further away, the longer the response time. By a second or two, but that could get the person shocked and potentially harmed. The GFCI cuts that time to less than 0.5 seconds. So that's why the GFCI finds its way into this article. This adds another aspect to the GFCI connection, meaning you don't have an AFCI. AFCI, you have to have AFCI breaker and AFCI outlet. GFCI, you just have to have the GFCI outlet, or in some cases, for some circuits, and inspectors don't love it when you do it, only the GFCI. Almost 100% of the time, they will ask for the outlet too, because of the worry is not that somewhere along the circuit there's a ground fault and a short circuit where I want the GFCI to breaker to trip. It's at the load when people are plugging things in and using the devices that I want to protect everyone. That's the main difference and why the GFCI finds its way. And now you can understand why it's water focused, because there's where potentially these hazards can happen, where loads are being plugged into. That's why the living room doesn't need a GFCI. There's nothing there that can potentially cause those harms. You know, in the bathroom, you're with a hairdryer or a shaver. In the kitchen, you're putting blenders around sinks. Garages, again, water potentially hazards. All right, let me pause the video recording right